Hello students. So I hope you must have seen the first video of introduction to this chapter, which contains all the useful terminology that we are going to use this chapter. So hoping that you know all the terms involved in this chapter, now we will move on to solve the exercises of NCERT book. This is exercise 1.1 and it has got 7 questions, so we will solve all of them today. So the first question says, express each number as a product of its prime factors. Product of its prime factors. So we have already discussed what are prime numbers. And in this case, we have to do the factorization of 140 in terms of its prime factors only. So let us start doing this. This is 140. See, we have already discussed all the divisibility tests of prime numbers. So starting from the very smallest prime number, 2 is the smallest even prime number. And the divisibility test says that if a number is having its unit digit as 0, 2, 4, 6, 8, those numbers are divisible by 2. So we can see that 140 is divisible by 2. So we get 70 by dividing 140 by 2. So now again checking for divisibility by 2, we divide 70 by 2. So we get 2 3s are 6, 1 joined with 0, 10, 2 5s are 10. Okay, now this number is not an even number because it has 5 at unit place. We cannot divide it by 2, so we go by 3. For 3, we check the sum of the digits. 3 plus 5, which is 8. 8 is not a multiple of 3. So this number is not divisible by 3. Next prime number is 5. So by checking the divisibility of 5, we can say that 35 is divisible by 5 because its unit digit is 5. It should be 5 or 0. So we divide 35 by 5, we get 7. And 7 is a prime number which is divisible by 7 itself. Right? So make sure that when you are dividing any number, you just have prime numbers on these division numbers. Right? So 140 can be written as product of 2 by 2 by 5 by 7. Right? This is called prime factorization. Next, we have 156. So we take 156 and start doing the prime factorization. Again, check with the divisibility of 2. This number is divisible by 2. So 2 sevens are 14. 1 combined with 6 gives you 16. 2 eights are 16. Still, this is divisible by 2. So we get 2 times 3 is 6. 1 combined with 8, 18. 2 nines are 18. Now we have got 39. 39 is not an even number. So we have to drop 2 for divisibility. Next comes 3. For 3, you check the sum of these digits. 3 and 9. That is 12. 12 is a multiple of 3. So we can divide 39 by 3. 3 ones are 3. 3 threes are 9. Right? So now we have got 13 and we know 13 is a prime number. It is divisible by itself only. Right? So the prime factorization of 156 gives you 2 multiplied by 2 multiplied by 3 multiplied by 13. Right? So this is called prime factorization of numbers. Next, we have a bigger number which is 3825. 3, 8, 2, and 5. Okay. If we start with 2, this number is not divisible by 2 because it's not an even number. Then we come to 3. For divisibility by 3, you can add these digits like 3 plus 8 plus 2 plus 5. That is 11 and 2. 11 and 2 is 13. 13 and 5 is 18. That means since the sum of the digits is 18, which itself is a multiple of 3, we can divide this number by 3. 3 ones are 3. 3 twos are 6, 22, 3 sevens are 21, and 3 fives are 15. Right? Now again, we have got a bigger number. Check divisibility by 2. Add the digits. This is 3 plus 7, 10, 10 plus 5, 15. So this number is still divisible by 3. So take 3 and now start dividing. 3 fours are 12, 3 twos are 6, and 3 fives are 15. Okay. Now again check the divisibility by 3, which is 4 plus 2 plus 5. 6 plus 5 is 11. 11 is not divisible by 3, so we have to drop 3 for the divisibility and take the next prime number, which is 5. Now if we divide 425 by 5, 5 eights are 40, 25, 5 fives are 25. This number is still divisible by 5, so we divide 85 by 5, 5 ones are 5, and 35, 5 sevens are 35. Now 17 is a prime number, so we can directly divide 17 by 17. So the prime factorization of 3825 gives us 3 times 3 times 5 times 5 times 17. Right? This is the prime factorization of 3825. Okay. Now we move on to the next number, which is 5005. Okay. Now this number is not divisible by 2. We can check it by checking the unit digit. Now we add all the digits, we get 5 plus 5, 10, which is not divisible by 3 either. So we take 5. For divisibility of 5, the unit place should either be 0 or 5, so it is. Now we divide this number. 5 ones are 5, 0, 0, 5 ones are 5. Right? Now this number is not divisible by 3 or 5. So the next number of divisibility comes out to be 7. Next prime number is 7. How do we divide a number by 7? Let's revise the divisibility. So it says that you have to take the twice of the ones digit. That means 1 multiplied by 2, that is 2. And then take the difference of remaining part of the number. We are left with 100. 100 and 2. Take the difference of these numbers, that is 98. Now, if this difference is 0 or a multiple of 7, then this whole number will be divisible by 7. So yes, the difference is 98, which is a multiple of 7. So we can divide this number by 7. 7 ones are 7. 3 combined with 0, 30. 7 fours are 28. 2 combined with 1, 21. 7 threes are 21. So now dividing this number by 7, we get 143. Now, if you check divisibility by 7, this will not be divisible. Like twice of 3 is 6 and 14 minus 6 is 8, which is not a multiple of 7. So next prime number is 11. Now, what is the divisibility test of 11? It says if this is a number like 143, you take the sum of the digits at odd places. Like this is first place, first, second, and third. The odd places are 1 and 3. Add the digits at first and third position. You get 1 plus 3, 4. And the digits at even position. We have only one digit at even position, which is 4 itself. Difference is 0. If it is 0 or a multiple of 11, then it is divisible by 11. So in this case, the difference is 0. We can divide this number by 11. So you get 11 ones are 11. Remainder 3 combined with 3, 33. 11 threes are 33. Now, 13 is a prime number, so we can directly divide 13 by 13. So the prime factorization of 5005 gives us 5 times 7 times 11 times 13, right? Okay. So now next number is 7,429. So see, we have already learnt divisibility rules till 11. After that, we have prime numbers like 13, 17, 19, and 23. So for bigger numbers, if a number is not divisible by the given prime numbers till 11, then we have to practice division by hit and 12 method and check by which prime number is this divisible. So after practice, you will see that it is not divisible by till 11, it is not, you can check it by divisibility test. After that, this is not divisible by 13. So next we have 7,429. We do it by 17. 17 fours are 68. 14 minus 8 is 6. Then we have 62. 17 threes are 51. This is 11. And then 17 sevens are 119. So this number is divisible by 17. We divide this number by 17, we get 437. Right? Now again we try this by 17. 17, try this 437 by 17. 17 twos are 34. 13 minus 4 is 97. This is not divisible by 17. So next we go by 19. 437 divided by 19. 19 twos are 38. 13 minus 8 is 5. 57. Yes, 19 threes are 57. Now we divide this number by 19. So we get 23. And 23 itself is a prime number. So we can divide this by 23. So the prime factorization of 7,429 becomes 17 times 19 times 23. Right? So these were the 5 parts of first question in which we have to do the prime factorization. Next question says find the LCM and HCF of the following pairs of integers and verify that HCM into LCM into HCF is equal to product of two numbers. Now we had studied this formula in the introductory video. So what we have to do is, again, we have to do the prime factorization of these numbers, like 26. 26 is 2 times 13 times 1. And next we have 91. 91 is 9 plus 1. This is 7 times 13 and 13 times 1. See, 26 can be written as 2 times 13 and 91 can be written as 7 times 13. So now here we will first learn how to find the HCF and LCM. HCF is highest common factor. So when we have got the prime factorization of numbers, we should be looking for the numbers, maximum numbers, which are common to both the prime factorizations. So in this case, we have 2 and 13 in 26, 7 and 13 in 91. So 2 and 7 are just in one of the numbers, but they are not common to both the numbers. So what we can see is 13 is a common number which is present in both the factorizations. So HCF is only one number, 13. Now in case of LCM, what do we do? In case of LCM, LCM is lowest common multiple. Lowest common multiple is some number which is maybe equal to 1 or bigger than both, but it is divisible by both the numbers. That means it should have all the factors which are present in the maximum numbers in both are given numbers like 26 and 91. So if we check 13 is common to both, so we can write 13 because the number will be divisible by 13 if 13 is existing in both the numbers. So the multiple which we are looking for, it will be having 13 as a common factor, right? Next, we have to look for a number which is present in either of the factorizations that we have to write in the maximum power it is existing in the presentation. So like check for 7. 7 is there in 91. It is not there in 26, but since it is existing once, we have to write it here. Okay, now both the factors of 91 have been taken into the consideration. Next, check for 26. 26 has factors 13 and 2. 13 we have already taken. And then we are left with 2. Now we have to, since 2 is occurring only once in 26, so we have to write it once. That means now you can see that a number which will be obtained by the product of 13, 7 and 2, that will be a number which is divisible by 26 and 91 both. It is a common multiple, right? So it should have all the numbers in the maximum quantity which are present in the prime factorizations of the two numbers. So if we solve them, we get 13 sevens are 91 and 91 times 2, 2 ones are 2, 2 nines are 18. The LCM is 82. So we have to do the verification. Verification means LCM into HCF. So LCM into HCF. Take the product of these two quantities. LCM is 182 and HCF is 13. So now I multiply these two numbers, 182 by 13. 3 2s are 6, 24 to 182. This is 6, 6, 3. This is 2366. On the other hand, we have to take the product of two numbers. Our two numbers are 26 and 91. Okay, now we do the product of 26 and 91. 6 ones are 6, 6 nines are 54. 2 ones are 2, 2 nines are 18. This is 6, 6. Yes, again we have got the same number, 2366. So this was the verification that when we take the product of HCF and LCM of the two numbers, it comes out to be same as the product of the two numbers themselves. So we can say that LCM into HCF of 26 and 91 is equal to the product of 26 and 91. Hence, we have verified. Right? So this was the first part of second question. Next is we have to perform the same operation on these two numbers, 510 and 92. So first we have to do the prime factorization of these two numbers. 2 2s are 4, 2 5s are 10 and 2 5s are 10. Now 5 plus 5, 10 plus 2, 12. This is divisible by 3. 3 8s are 24, 3 5s are 15. 5, 17, 17, 1. Next we have 92. 2 4s are 8, 2 6, 7, 2, 23. And 23 itself is a prime number. So when it comes to prime factorization, the prime factors of 510 are 2, 3, 2 times 3 times 5 times 17. And then it's 92. 92 is 2 times 2 times 23. Right? Now we will find HCF and LCM of these two numbers. HCF is the highest common factor. So we have to look for the common numbers to both the presentations. Yes, a 2 is common. Then 3, 2, 5, 23, 17. Then no other number is common to both the prime factorizations. So HCF is the only number 2. Right, now we come to LCM. Regarding LCM, I told you the numbers which are common have to be written once. Like 2 is common to both the presentations, so 2 will be written once, right? But the rest of the factors which are occurring either in 92 or in 510, they have to be there as many times as they are occurring in the prime factorization. So like we come to 2. Now 2 is only in 92, but since the common thing has been taken as once, this has nothing in common, so it should be taken once. Then we go to 3. 3 is there in 510. It is only once written in the presentation, so we write it here once. Then we go to 5. 5 is there in only one number, so write 5. Then we go to 17. 17 is occurring in the prime factorization of 510, and that is only for one time. Same is the case with 23. So the crux is numbers which are common, they have to be written. And apart from that, the numbers which are not common, they have to be written in the LCM as many times as they are occurring in the prime factorizations of either of the numbers. Now, to find the LCM, we have to take the product of all these numbers. 2 times 2 is 4, 4 3s are 12, 12 5s are 60, right? So 60 times 17 times 23. So we take the product here, 23 times 17. 7 3s are 21, 2, 14 and 2, 23. 391 and 391 multiplied by 6, 6 are 54, 5, 18 and 5. This becomes 2, 3, 4, 6, 0. Right? This is our LCM of these two numbers. So we have found HCF and LCM. Now we have to verify the relationship. We have first to take the product of HCF and LCM. That means 2 multiplied by 2, 3, 4, 6, 0. What it should be? This is 2, 3, 4, 6. 0 times 2, 0, 12, 9, 6, 4, which is 4, 6, 9, 2, 0. Right? Now, on the other part, we have to find the product of two numbers. Product of two numbers is 510 multiplied by 92. So we take the product of 51 and 92. 2 ones are 2, 2 fives are 10. 9 ones are 9, 9 fives are 45. 0, 2, 9, 6, which is 4, 6, 9, 2, 0. Right? So again, we have got the same result in the products of, on the one side, we have taken product of HCF and LCM. On the other side, we have taken the product of the two numbers. So we have verified that the HCF and LCM of two numbers is equal to, here HCF and LCM of 510 and 92 is equal to the product of these two numbers, 510 and 92. Right? So now our next sum is 336 and 54. So we first have to find the HCF and LCM of these two numbers. For that, we do the prime factorization. 336. 2 ones are 2 6s are 12, 2 8s are 16. 2 8s are 16, 2 4s are 2 42, 21, 3 7s are and 7 1s are. And next we are doing 54. 2, 27. This is divisible by 3 9s are, 3 3s are, and 3 times 1. So the prime factorization of 336 is 4 times 2 multiplied by 3 multiplied by 7. And then in 54 we have 2 multiplied by 3 times 3. Right? Now factorization part is over. Then we have to find the HCF. HCF is we have to look for the common numbers, and we have 2 and here we have 3. So the common factors are 2 and 3. So the HCF becomes 6, right? And then we have LCM. LCM is, see, for the LCM, first you have to write the numbers which are common. So we have 2 and 3. These are the common numbers. After writing them, then you look for the numbers which are not common to both the terms. Like we have these 3 2s in 336. Apart from these common numbers, 2 is occurring 3 times extra in 336. So we have written 3 2s. Then you take these 2 3s in the prime factorization of 54. So now we are left with 7. So now we have considered all the factors. First of all, these two were the common factors. After that, which are not common, even they have to be written as many times as they are occurring in the prime factorization of either of the two numbers. So for LCM, we have to take the product of 1, 2, 3, 4 times 2 is 16. 3 times 3 is 27 and then 7. So I take 27 times 16. 7 6 are 42. 6 2s are 12 and 4. 16. This is 27. 7 and 6, 13, 1. 432 multiplied by 7. 7 2s are 14, 21, 22, 2. And 7 for the 28 and 2 is 3024. Right? So the LCM becomes 3024. Now, HCF and LCM are there. Now we have to do the verification part. Now take the product of HCF and LCM. HCF is 6 multiplied by 3024. Now we multiply 3024 by 6. 6 4s are 24, 2. 6 2s are 12 and 2 14. 6 3s are 18. This is 18144. Right? The product of HCF and LCM are 18144. Now we have to take the product of these two numbers, which is 336 and 54. Okay. So we have 336 and 54. 4 6 are 24, 2, 4 3 are 12 and 2 14, 1, 12 and 1, 13. 5 6 are 30, 3, 5 3s are 15 and 3, 15 and 3, 18, 1, 5 3s are 15 and 1, 16. So we have 4, 4, 1, 8, 1. So we can see that again the product of these two numbers is equal to the product of their HCF and LCM. HCF and LCM of 336 and 54 is equal to the product of 336 and 54. Right? So this is the verification of the formula. Now we have third question. Find the LCM and HCF of the following numbers integers by applying the prime factorization method. Right? So we have to do the prime factorization of all the numbers first. 12. This is 2 6 are 2, 3s are and 3 times 1. Then we have 15. This is divisible by 3, 5, 1. And then finally we have 20. Finally we have 21. which is 3 times 7 and 7 times 1. So when we write 12, this can be written as 2 times 2 times 3. Then it is 15. 15 is 3 times 5. Finally, we have 21, which is 3 times 7. Right? So now we have three numbers for which we have to find the LCM and HCF. We go for HCF first. Look for the number which is common to all the three numbers. See, 2 is only in 12, not in 15 and 21. A 3 is here, a 3 is here, a 3 is here. So, common factor is only 3. So, HCF is 3 in this case. Now we come to the LCM part. LCM part, I have already told you, whatever is common, you have to write it once. That's it. After that common number, look for the numbers which are not common. Like we have two 2's in 12, write them 2 times because it is occurring 2 times. Then 3 we have already taken. Then come to 5, which is present only in 15. And then lastly, it is 7, which is present only in 21. This is the way we find LCM, right? So take the product of all these numbers. 3 2s are 6, 6 times 2 is 12, 12 5s are 60, 60 into 7 is 420, right? So this is the HCF and LCM of these three numbers. Next we have 17, 23, and 29. Just by looking at these numbers, you can say that all of the three numbers are prime numbers. So we have no prime factorization of these numbers because they are prime. 17 is 17 into 1, 23 is 23 into 1, and same is the case with 29. It is 29 into 1. So if they cannot be broken down into the prime factorization of other numbers, they have only two factors, 1 and the number itself. So the HCF of these numbers is nothing but 1, which is common to all the three numbers. Now we come to find the LCM of these numbers. It is simply the product of these three numbers. We have learned in junior classes that if we have prime numbers, the LCM is simply the product of those numbers. 17, 23, and 29. So 29 multiplied by 23, 27, 2, 3 2s are 6, and 2, 8. This is 29 times 2 is 58. 7, 6, 6, 7 multiplied by 17. 7 sevens are 49, 4, 42, and 4, 46, 4, 42, and 4, 46. And here we have 6, 6, 7, 9, 3, 3, and 11. So this is the LCM is 11339, right? This is the LCM of these numbers. Next we have three numbers 8, 9, and 25. So for this, we have to do the prime factorization, which is 2 times 4, 2 times 2, 2 times 1. About 9, we have 3 times 3 is 9, and this is 1. So this is, next we have 25. 25 is the product of 5 and 5. So we write the prime factorization of these numbers. 8 is 2 times 2 times 2. Then 9 is 3 times 3. And 25 is 5 times 5. Okay, now this is again, you can see that there is no number which is common to all the three numbers. So When this is the case, we write that HCF of these numbers, because since 1 is the factor of every number, we can write it like this. So HCF automatically becomes 1. They are co-prime numbers. Co-prime means they have no common factor. So the HCF of co-prime numbers is 1. And next we have to take the LCM. For LCM, since there is nothing in common, we have to take the product of all the three numbers, like 8 multiplied by 9 multiplied by 25. So 25 times 8 is 200. 200 into 9 is 1800. Right? So now this was the LCM of these three numbers. Next we have, given that the HCF of these two numbers is 9, find the LCM. So what we have to do is, we have already learned the formula that the product of HCF into LCM of these two numbers, that is 306 and 657. It should be equal to the product of these two numbers, which is 306 into 657. We have done this formula in question number 2. So since we have verified, you can use this formula to solve the questions. Now, given that HCF of, you are given these two numbers 306 and 657. They have given that HCF of these two numbers. So I am simply writing it, HCF into LCM is equal to the product of these two numbers 306 into 657. HCF, they have already given that it is 9. To just put the value HCF as 9, and then LCM becomes 306 multiplied by 657. So here, to find the LCM, we take this 9 to the right hand side, which comes into division, right? Now, instead of taking the product first and then dividing it by 9, you should just write it down, reduce it first, and then take the product finally. So, see, this is 6 plus 3, 9. Sum is 9, so it is divisible by 9. 9 3s are 27. 36, 9 4s are 36. So the LCM of these two numbers is equal to the product of 34 and 657. Right? So 657 and 34. 4 sevens are 28. 2, 4 fives are 22. 22, 2, 6 fours are 24 and 2, 26. 3 sevens are 21. 2, 3 fives are 15 and 2, 17. 7, 1, 3 6 are 18 and 1, 19. 8, 3, 3, 2, 1. That is double 2, double 3, and 8. Right? So this is the LCM of these two numbers. Next we have the sum. Okay, now next question is, check whether 6 to the power n can end with digit 0 for any natural number n. Right? So we have to check if we have different powers of 6. Like 6 to the power 1, we know that it is equal to 6. Right? And 6 to the power 2 is 36, and so on. So the question is asking that you have to check whether these different powers of 6, will any of these powers end with 0 at the unit place, right? So instead of, we cannot do keep doing multiplications like this. So we have to check in all, like 6 can be written as 2 multiplied by 3. The prime factorization of 6 is 2 into 3. Now, if we consider 6 raised to the power n, that means we can write this as 2 multiplied by 3 raised to the power n. right? So from here we can see that this is 2 to the power n multiplied by 3 to the power n. So he's asking whether we can have 0 at the unit place or not. We know that we know that for a number to have 0 at unit place, unit place, we should have we should have 2 multiplied by 5. We should have a combination of 2 and 5, since we can have multiple prime factors. But if a 2 and a 5 is present in the prime factorization of a number, then we can say that we will be having at least 1 0 at the unit place. At the unit place, we will have 0. So we can see that the prime factorization of 6 does not contain any 5. The prime factorization of 6 does not have any 5. So we can say that, so 6 to the power n, any power of 6 will not end with 0 at the unit place, right? Matlab, you must have seen that whenever you require 0 at end, at least 1 0 at unit place, we should have 1, 2 and 5. 2 and 5. Product of 2 and 5 makes 10. So for 1 0, we should have 2 and 5 both. But this in this prime factorization, we have n times 2, but there is no 5 present in the prime factorization of this number. So it will never end up with 0 at unit place. Next question is, explain why these numbers 7 times 11 times 13 added to 13 and this number, they are composite numbers, right? We have to prove that they are composite. So what are composite numbers? We have learned in the first video that a number which is not prime means it has other factors except 1 and the number itself. So we need to prove that they are divisible by other numbers except themselves and 1. For that, the first number is 7 times 11 multiplied by 13 added to 13. Now what we do, we just take different terms before addition, after addition. So we have two terms in this expression. We can see that 13 is common to both the terms. So if we do the factorization of this expression, which has two terms, we can take out 13 as the common factor. And after that, what we are left with, we are left with 7 and 11 at the first place. And then after addition, we have only 1. So now we can see that 13 is multiplied by, even if you want to solve it, otherwise you can leave it here also. This is 77 plus 1 or 13 multiplied by 78. So you can see that the whole number that was given in the form of an expression can be written as the product of these two numbers. And since this number can be written as a product of two numbers, so we can say that this is a composite number, right? So the given number can be written as the product of two numbers. So it is composite. It is composite, right? Similarly, we can do with the second sum here, which is 7 times 6 times 5 times 4 times 3 times 2 times 1, right? Added to 5. Basically, they have given this number in the form of two terms. We have an expression in which we have two terms. Again, instead of taking the whole product, we can first factorize this number. We can see that 5 is occurring here and here in both the terms. So 5 is common. After taking out 5 common, we can take the product of 7 times 6 times 4, 3, 2, 1. And after that, in addition, we have 1. So you just solve it. This is 7 6 are 42. 42 times 42 times 24. 42 times 24 is 2 4s are 8, 4 4s are 16. 2 2s are 4, 2 4s are 8. 8, 1008. 1008 added to 1. So we can write this as this is 5 times 1009. So we can write here as, since again the whole expression can be written as the given number can be written as the product of two numbers. That means whatever the number is, whatever we get the product of this number is, this is divisible by both. The number will be divisible by both 5 and 1009. So we cannot say it is a prime number. So it is composite. Right? So to prove a number composite, we just need to prove that it can be broken down into factors, or it can be written as the product of two or more numbers. Then it becomes a composite number. And lastly, we have a problem. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field. Right? So write it down. Time taken by Sonia to go one round. That is 18 seconds. 18 minutes. Sorry. 18 minutes. Now, to drive one round of the field, while Ravi takes 12 minutes for the same. Now, time taken by Ravi. Ravi to go one round. That is 12 minutes. Right? For the same. So, just consider this. Like this is a circular field. Now, Sonia takes 18 minutes to cover one round of the circle, and Ravi takes 12 minutes to complete one round of this field. Now, suppose they both start at the same time and go in the same direction. After how many minutes will they meet again? So let's see, Sonia and Ravi both they start at the same time. So in one round, Sonia will be here after 18 minutes. Sonia will be here. Ravi will be completing this round in 12 minutes. So he will be ahead by 6 minutes like this. He will be here. So we can consider that Sonia is taking 18 minutes to complete one round, but Ravi is completing one round in 12 minutes. So after 12 minutes, 18 minutes, he will be here, but Sonia will be here, right? Like they are starting at the same position A. After 18 minutes, Sonia will finish one round. But Ravi is taking less time to complete one round. So if Ravi and Sonia both start after 12 minutes, Ravi will complete this round, and in next 6 minutes he will be here. He will be ahead of Sonia because he is driving fast, right? But now in the second round, Sonia will complete it in the next 18 minutes. So after 36 minutes, Sonia will again be here. But now Ravi is taking 12 minutes to complete this round. So in 12 minutes, it will be one round. In 24 minutes, it will be second round. In 36 minutes, it will be third round. So, but since these numbers are small, we can do them orally. Otherwise, what we have to say is, what is the common number or common time at which they will meet at their initial position? And that for that, we have to take the lowest common multiple of the numbers which they take to cover one round, right? So LCM of LCM of 18 and 12. You have to find the LCM of 18 and 12. Now prime factorization of 18 can be given as, this is 2 times 3 times 3, and prime factorization of 12 is 2 times 2 times 3, right? So the common multiple is LCM of these two numbers will be, like, write down the first common numbers, like this 2 is common, 3 is common. I write them first, 2 and 3. Now which are not common are 1, 3 and 1, 2. You also take them once. So after getting these numbers, we have 6 times 6, that is 36 minutes. That means if they are starting at the same time, see, after 36 minutes, you can check that after 36 minutes, Sonia will be finishing her two rounds of the circular field. And she will take two rounds in 36 minutes, and Ravi will take 12 multiplied by 3, three rounds in 36 minutes, right? So after 36 minutes, both of them will be completing an integral number of rounds. They are not in fractions. They will exactly be at the same position from there where they had started. So whenever we have to find number, like two or three persons are starting from the same time, or we have questions which involve the bells, two or three bells ring at the same time, and they have different intervals. When we again have to reach to the common number, we always go for the LCM. That will be the common multiple of those different steps or different timing intervals or different durations. So we take the LCM of these numbers. At that point, after 36 minutes, both the drivers will be at the same position, irrespective of the number of rounds they have taken. But they will be at the same position, right? So we go for LCM in such numbers. So I hope this is clear now. So this is all for this video. We have completed exercise 10.1 today. And in the next video, we will be doing exercise, sorry, it's 1.1. And in the next video, we will be doing exercise 1.2. Thank you for watching my video, and we will meet in the next video.